we've been doing a lot of formula writing and naming of compounds, and now we're going to talk about um, what actually happens to make those compounds. Like we have covalent compounds, carbon dioxide, and why do carbon and oxygen bind together? Or ionic compounds like sodium chloride, why do sodium and chlorine bind together? And that's called bonding, and it's all about electrons. Right? And what's important to us is just those outer electrons and how much the atoms that are bonding really like electrons. And remember that you should have this somewhere on your periodic table. The concept of electronegativity, how much an atom loves electrons, how strong of a pull it has on its own and on other nearby atoms' electrons. And francium is the least electronegative down here in the lower left-hand corner. And electronegativity, or the love of electrons, increases as you go up the periodic table and as you go to the right. And you get all the way up here to francium, or to fluorine, and it's the most electronegative. But you see, all of these non-metals, including hydrogen over here, are very electronegative. They all have a strong pull on their electrons and on other electrons and atoms that come nearby. So that's an important concept to us. And then the valence electrons, which are the electrons that are on the outside of the atom, the outside S and P. And so if you remember, that first group in the S's has one valence electron, two valence electrons for the second group, and then 3, 4, 5, 6, 7, and 8. So everything in those group, that's how many valence electrons, how many outer shell electrons they have that are able to bond and interact with other atoms. And remember that helium and hydrogen are the exception. Helium only has 2 valence electrons, even though it's over there in that noble gas group where they all have 8. And it's also important to note that everything wants 8 valence electrons. That's why the noble gases way over there on the right-hand side, they don't really react. And when we do when we go back and look at electronegativity, that arrow doesn't point to helium as being the most electronegative, or neon, or any of the noble gases, because they don't have a strong want of electrons. They hold on to their own very well, but they're not going to pull electrons from other atoms. Okay? So it's important to know how many valence electrons every single atom has, and the one exception, that is helium. All right, so here we're going to start talking about before we really get into bonding and the shapes that things have. We're going to talk about Lewis dot structures, and don't worry too much about the name. Lewis is the person who came up with it, and it's dot structures, and the dots are just electrons, valence electrons. So we'll start here by doing the Lewis dot structures, the electron structures for just atoms, not something in a compound, but just individual atoms. And all you have to do is basically think of the atom almost like it has a square around it. Each little symbol, like here's oxygen, just think of each of the 4 sides around it, almost like a tile on the periodic table. And you're just going to place its valence electrons around it. You're going to put one on each side until you get each 4 sides has one, and then you'll start doubling them up. And all you have to do is determine how many electrons each one has. And if you look at oxygen, it's in that 6th group there, and it has 6 valence electrons. So you're just going to put them around the outside, 1, 2, 3, 4, 5, 6. And that's it. And you're looking at as though there's a square around the symbol, and you're going to put them on each side, and each side basically represents an orbital. And remember, the valence electrons are the S and P orbitals. So each row has 1 S and 3 P orbitals. So that's 4 orbitals, except, of course, hydrogen and helium in the first group that only have the 1 S orbital. Here, we'll go over to oxygen with a 2- charge. That means it's gained 2 electrons. So instead of 6, it has 8. And all you're going to do is put its 8 electrons around it, 1 on each side. until every side has 1, and then you start to double up the electrons. And now this is 8 valence electrons around oxygen 2 minus, and that means it's more stable. Oxygen has gotten to the 8 valence electrons that it wants, like everything wants. We come down to here to sodium. It's in the first group. That's 1 valence electron, so it only has 1. And remember, these are electron structures, so we're just putting the valence electrons around the symbols so that we can use them for bonding, for a covalent and ionic bonding. We go to neon over here. It's 8 valence electrons. Again, just like with O2 minus, you simply put the 8 electrons, 1 on each side, until each side has 1, and then you start doubling them up. Neon has 8 valence electrons, and so it has 8 valence, 2 on each side. Helium has 2. Remember, it's happy with its 2, and there is no p orbital in that first row. There are no p orbitals, so it's just the s's, so those 2 can go by themselves on one side. Helium doesn't have the other 3 sides, the other 3 orbitals. It only has the s orbital. And no, it doesn't really matter which side you put the electron, which one you start on. It doesn't really matter. I started for sodium. I put one here. I could have put it here or here or here. It doesn't really make any difference. Carbon has 4 valence electrons, so you would simply put its 4 electrons, 1 on each side, around it. And that's how you do the Lewis dot electron dot structure for individual atoms. Now, if we're talking about where they're not individual atoms, they're molecules, this is what's important to us. It's basically the same thing. You're just doing it for, and we'll go through it step by step here in a minute. But if you look here, like this is water, so it's an oxygen plus 2 hydrogens. Oxygen, and then we'll talk in a minute why oxygen goes in the middle. But it's surrounded by the 2 hydrogens, and it has a pair of electrons between the oxygen and each hydrogen, and then they have these 2 pairs of electrons. And remember, hydrogen has 1, so there's hydrogens 1, there's hydrogens 1. Oxygen has 6, so it's 1, 2, 3, 4, 5, 6. So that and when you show them in a molecule, you don't keep them the way as just as dots. If you have electrons in between atoms, they're just shown as a line. The line still means 2 electrons, but it means that they are bonded. So right here is a bonding pair. Right here's a bonding pair, and here are lone pairs. Okay, and the key is that 8 electrons, or the full octet of electrons around everything. Oxygen wants 8. Remember, hydrogen and helium, they're exception. They only want 2. We go over to HCl. Cl has its 8, 3 non-bonding pairs, and a bonding pair. Hydrogen is happy with its 2. And so if we go to CO2, there's 4 around carbon and 6 around each oxygen. And it's not always just 1 bonding pair of electrons. Sometimes it's 2. Like between carbon and oxygen, it requires 2 bonding pairs. So this is a double bond between carbon and oxygen, and another double bond between this carbon and oxygen. But every one still has its 8 valence electrons around it. So let's talk about how this is done systematically. So Lewis dot structures for covalent molecules. Remember, covalent means 2 nonmetals. So we have hydrogen and chloride here. This would be hydrogen monochloride. Step 1 is to just simply count how many valence electrons this molecule has in total. Hydrogen is in the group with 1, and chlorine is in the group with 7. So there's 8 total valence electrons. So you're going to draw a structure that has all 8 valence electrons bonding H and Cl together and around the atoms, so that both of them have their full octets. So 8 of them for chlorine and 2 for hydrogen, because it and helium are the exception. So the second step is to put the least electronegative element, or the lone element, in the center, but hydrogen is always the exception. In this case, hydrogen is less electronegative than chlorine, But if you look on the periodic table, remember the arrow points up to fluorine. Hydrogen is way over to the left, but it's actually a nonmetal. But even though hydrogen is less electronegative, it always goes on the outside for all molecules. So here we have hydrogen and chlorine. The third rule is you put a bonding pair of electrons between two atoms. So you've got to bind them together, right? And then you're going to take all the other electrons. So we have 2 here bonded between H and Cl, but we have a total of 8. So we're going to take the other 6 electrons and we're going to place them around in pairs around the outside atom. And remember, hydrogen already has 2 around it, these 2. That's all at once. But chlorine needs 6 more. So you're simply going to place them around the chlorine atom. And then that's it. You're just trying to make everybody happy. You're trying to complete the octet or the duet for hydrogen. And then bonding pairs are just going to be replaced with a line. So instead of 2 dots, it's going to be the line that represents that it is a bonding pair of electrons. And now if you look around chlorine, if you draw a circle, sort of an imaginary circle around chlorine, chlorine has 2, 4, 6, 8. It has its 8 electrons. And you draw a circle around hydrogen, it has its 2 electrons, so everybody's happy. There's a total of 8 valence electrons, and all atoms have their full outer shell. Right, so let's try another one, water, H2O. Right, the rule is you're going to count the total number of valence electrons. It's 1 for each hydrogen and 6 for oxygen, so a total of 8 again. And then you're going to place the least electronegative element in the middle, except that hydrogen is an exception. In this case, hydrogen is the least electronegative, but hydrogen always goes on the outside. So you'll put the oxygen in the middle, the lone oxygen, and the 2 hydrogens around it. The third rule is to place a pair of electrons between atoms. So put a pair of electrons between O and H here, and a pair of electrons between O and the other H. So that's the 2 bonds. Okay? And the fourth rule is we're going to complete the octets on the outside atoms. Well, if you look around hydrogen, it has its 2, its duet, and so does this hydrogen. So they're happy. And now all we have to do is place the rest of the electrons around the central atom to complete its octet and use up all the valence electrons. We have a total of 8 we're supposed to use. We've only used 1, 2, 3, 4. So we have 4 more to put around the central oxygen. And then we're going to turn those bonding pair dot electrons into lines. So now we just need to look around each atom. We've used all 8 valence electrons. If we draw an imaginary circle around hydrogen, it has its 2. It's happy. This hydrogen has 2. It's happy. Oxygen here, if we draw a big circle around here, there's 2, 4, 6, 8 valence electrons. So every atom has its outer shell full, and we've used all 8 valence electrons. All right. NBr3, another example. Count the total number of valence electrons. Nitrogen has 5. In each of the bromines has 7, so that's a total of 26. All right? We're going to put the least electronegative or the lone element in the center. The lone element is nitrogen, and we're going to put it in the center. It's easier to look for the lone one than it is to go look for the actual electronegativity values. But we have N in the middle, and we're going to draw those 3 bromines around it. So NBr3. Remember, we're going to put bonding pairs of electrons in between each of the atoms and each N and Br. And that right there is 6 of our total 26 electrons. The next rule is we're going to complete the octet on the outside atoms first by putting bonding pairs of electrons, counting them until we get to the total 26. We already have 6, and we're going to put bonding pairs around the bromines, and then we'll move and put them around the nitrogen, and then we will replace those bonding pairs between the atoms with lines. So we have, like, each bromine has 3 non-bonded pairs around it and 2 bonded pairs. So around each bromine is 8 valence electrons, if you check them. And then if you look at the nitrogen, it has 3 bonded pairs plus 2, a lone pair of non-bonded electrons for a total of 8. So every atom has its octet full, and we've used all 26 valence electrons. So this is the Lewis dot structure for nitrogen tribromide. All right. Now, that was for covalent bonds, and that's what we're going to deal with when we start to deal with the shape. Like, what's important to us is not just that this is the dot structure for NBr3, but we want to know what physical three-dimensional shape this molecule takes, and that'll be our next step as in the next couple of days. But here, that for covalence, what that means is basically, if you look at, like here, we have SiO2, silicon dioxide. Silicon is way up here, okay, under carbon, and oxygen is up here. Oxygen is definitely more electronegative, but it's not electronegative enough to pull electrons from silicon. So since they're both nonmetals, silicon and oxygen, and they're both highly electronegative, covalent compounds end up sharing electrons because they're not strong enough to take them from other atoms. So here, if you look, oxygen has 6, but it wants 8. This oxygen has 6, but it wants 8. So they both want to take 2 more electrons. Silicon has 4, and it wants 8, like everything else. It wants 8 valence electrons. It wants to fill that octet. So it needs 4 more. Now, neither silicon and oxygen are strong enough to take electrons from each other, so what they do is they share. So each oxygen will share 2 electrons with silicon. This is a covalent bond. This is the sharing of electrons between 2 nonmetals that are not electronegative enough to steal them from each other. They both really like electrons. They have strong electronegativity, so they have to share. So this is silicon dioxide. And if you'll draw a circle around each one, without gaining any electrons, without actually taking them from anywhere, each atom has garnered its 8 valence electrons by sharing with each other. Okay? Draw a circle around each one. They all have 8 valence electrons. And that means that those electrons are literally shared. They buzz around the atoms in shared orbitals. Okay? Now, if we're talking about ionic compounds, this is different. This isn't 2 nonmetals. This is a metal and a nonmetal. If you look at oxygen up here, still really electronegative, really strong pull on electrons. And beryllium here is way over here to the left, low electronegativity. So the difference between covalent, where they share them, where the electrons are shared, because they're all really strongly electronegative, and ionic is you have a strong electronegative nonmetal and a weak electronegativity metal. So oxygen has 6 valence electrons, but it wants 8. Beryllium has 2 valence electrons. It wants 8, but it isn't strong enough to hold on to electrons or take any. So beryllium over here, the way it gets a full outer shell isn't by taking electrons or sharing them. It gets a full shell by losing its 2 valence electrons to the really strongly electronegative oxygen. So the low electronegative metal will lose electrons to the high electronegative oxygen. So remember, for covalent, it's sharing. For ionic, those electrons are taken. They're stolen. This is the not nice type of bonding. And when oxygen takes 2 electrons, it becomes -2. It becomes a negative little magnet. And it gets its full outer shell of 8. Beryllium gets its outer shell by losing those because now it has helium's outer shell of 1s2. But in losing 2 electrons, it's now a +2. So we have a negative magnet and a positive magnet. And they are attracted to one another, and they stick and neutralize that charge. So this is beryllium oxide. So covalents stick together because they share electrons to get the full outer shell octet. Ionic compounds get to the full outer shell octet by one of them stealing electrons from the other and making a charge. So ionic is charges because electrons are stolen. Covalent is not charges because the electrons are simply shared. Let's do another example here. We have sulfur way over here, highly electronegative, really likes electrons, and potassium's way over here on the left, weak electronegativity, doesn't really have a strong hold on its electrons. Potassium has 1 valence electron, each of them. Sulfur has 6. They all want that full outer shell, but sulfur is strong enough to take those electrons from potassiums, making the potassiums, leaving them positive, leaving the sulfur negative. They're like little magnets that now stick together to neutralize each other, so this would be called potassium sulfide. And it's because electrons are stolen from the metal by the nonmetal. Okay, now there's a little bit of homework for you. Lewis dot structures, the top is where you're doing Lewis dot structures for just atoms, like O, B, E, Al. And in the bottom, you're going to go through those rules, those steps, where you count the total number of valence electrons, you put the least electronegative in the middle, and then you go ahead and put the lone pair, or the bonding pairs and the lone pairs until you add up the total number of valence electrons, making sure you have every atom have a full outer octet or duet for hydrogen and helium. So give that a shot.